Welcome back. Today we're going to revisit our economic application purchase under budget constraints and see how we can apply the Karush Kuhn and Tucker or KKT theorem to that setting. Let's quickly recap what the problem statement was and how we have to generalize that to be able to apply KKT. So this is going to be another example. Purchase under budget constraints. You do remember the setting that we had? We had products 1 to n. Each product has a specific price. We label these prices alpha 1 to alpha n. And that yields a price vector A that just consists of all these alphas. So it looks like this here, alpha 1 to alpha n. We have a budget available. We denote that one by beta. And there is a desired purchase that we would like to do. So we'd like to purchase x1 bar units of good 1, x2 bar units of good 2, and so on, up to xn bar units of good n. Okay, so this is the purchase that we would like to do, but we cannot afford our desired purchase. So again, the problem is if we compute A transposed x bar, so in other words, the sum of the alpha I times xi bar, so that's the price of the desired purchase, that is larger than beta, so this desired purchase does not fit into our budget. And we like to find a purchase decision that is close to our desired purchase, but satisfies budget constraints. Okay, so the desired purchase is not possible with our budget beta. So our task is find a purchase x star, again with x star 1 to x star n for each of the items here, close to x bar that satisfies budget constraints. And you remember we already had an optimization model for that. We wanted to minimize our objective f of x, and that objective was the norm of x minus x bar squared, or if we write this in vectorial form, x minus x bar transposed x minus x bar. So that was our objective function. And we wanted to optimize that subject to, and here we change a little something now, subject to A transpose X. We want this to be less or equal to beta. So in the original model, that was ATX equals beta. So we wanted to spend the whole budget. And this time we'll add the more natural restriction that we don't necessarily have to spend the whole budget. We just have to stay within budget. So the natural restriction here would be A transpose X is less or equal to beta. Now that means in our KKT formulation we'll define a function g as g of x equals ATX minus beta, and we constrain that to be less or equal to 0. Yeah, so this way we have a problem for minimize a function f subject to a function g of x less or equal to 0. Okay, and if we do that, then we will be able to apply Karush Kuhn Tucker. Now let's do that and see how that differs from our Lagrangian multipliers idea that we tried before. So in other words, we'll see what influence this more general setup will have on the results that we get. Okay, first thing we need to do is, again, we need to compute the gradient of f and also the Jacobi matrix of G. So gradient of f, we already did that before. That was 2x minus x bar, as you'll hopefully remember. As for the gradient of G, we also did that before. So the Jacobian of G, let's write it this way, of x. Remember, G is the function A transpose x minus beta. So basically, the Jacobian is just A. Okay, so let's find the KKT points. First condition for the KKT points, if you remember that, is the gradient of f of x plus the Jacobian of G at x transposed the multiplier, and for that multiplier we usually use y, a vector y. So it's like this here, that is 0. In this setting, what that means is our gradient of f here, that is 2x minus x bar, plus the Jacobian is just the vector a, and we only have one real valued constraint here, so we only have one multiplier. We'll just use the name y for that. Okay, so this is just a real number here. Okay, so that is the first condition. Second and third condition are feasibility. The second condition is g of x equals is less or equal to 0, or what that means here is ATX minus beta is less or equal to 0. Third condition is feasibility for equality constraints. There is no equality constraints in this problem, so that's not relevant. Fourth condition is our y is greater or equal to 0. And finally, complementarity constraints. For those, we have y transposed g of x is equal to 0. Or in this specific setting that we have here, what that means is y, our multiplier y times a transposed x minus beta is 0. Or, well, it's either y has to be 0 or a transposed x minus beta has to be 0, or both, of course, yeah, but at least one of these has to be the case. And that's where we start our analysis. We already know about the second case, ATX equals beta. That's exactly the case that we've analyzed in our equality setting before, right? So the only remaining question basically is what happens if the multiplier is 0. So we'll first investigate that. What about the case that the multiplier y is 0? So let's scroll back, have a look at the restrictions here. Now if y is 0, then of course this fourth constraint here, that is fulfilled. There's no y in the second constraint, so we don't have to care about that right now. In the first constraint we have a y, so this is something that we need to fulfill. Let's write down what that means. So what that means is, from the first condition we get 2x minus x bar equals 0. Well, but what does that mean? That of course means can only happen if x equals x bar. But we already know that for x equals x bar, this constraint here cannot be fulfilled. Okay, so let's make a note of that. But then ATX equals ATX bar, and that is greater than beta. And that's a clear contradiction. So what KKT tells us here is that case 1, y equals 0 cannot happen. Okay, so this case cannot happen. So what that means is we're back at the case where ATX minus beta equals 0, and that's precisely the same setting that we already got for the equality constraints. So that's our setting of minimize x minus x bar norm squared subject to ADX equals beta. And before you solve this, we have solved this already. And just to recap, the results of this case were, well, we get a multiplier of 2 over a norm squared times a transpose x minus beta, and we get optimal values x star as x bar minus a over a norm squared times a transposed x bar minus beta. Of course, there's a bar up there as well. Okay, so those were results that we derived already in one of the earlier videos for that equality case. And as it turns out, even in the more general setting where we allow inequalities here, it turns out we always automatically get back to the equality case. So KKT automatically tells us we'll always use the full budget. And of course, that is precisely what you would expect, right? You cannot do better by not using all possibilities that you have. So the best thing you can do here is you'll have to use the full budget to get a good decision. Okay, so that completes this economic application for the more general case of the KKT theorem. Thank you for your attention.